Okay, so in this first podcast of our last unit, we're going to be talking about some potential energy diagrams. You can see a few examples on pages 8 and 9 already. It's these kind of hill graphs. We're going to be learning some important points on them, how to read them, and what it tells us about chemical reactions. And starting from the top, overall, what they tell us is that the potential energy diagrams show us how much stored or potential energy is changing throughout a chemical reaction. So these generally have something like reaction coordinate or reaction progress as the x-axis, and then energy or potential energy on the y-axis. So we just see that energy change as we go through a reaction. Now, a reaction can technically go forward or reverse. We've learned that, talked about that some. If you take AP Chem, we will talk about that a whole lot more. But the forward reaction, like we would generally expect, would start with the reactants and end with the products. When we talk about something as the reverse reaction, then it's the opposite. We're kind of sort of starting with what we previously referred to as products, and we're going to be ending and forming the reactants. And this is a little bit counterintuitive because we're calling them reactants and products still. Oftentimes, because it's written and we read things from left to right, we still kind of refer to those as reactants and products. We could rewrite the whole reaction to flip them, but we can also just visualize it going in reverse with an arrow pointing the opposite direction. Now, where this ties into energy is if the forward reaction is exothermic, like I already had show up here, then the reverse of that reaction is going to be endothermic. So as we flip the direction of the reaction, we flip the direction the energy is moving. Kind of makes sense. That means if the forward reaction is endothermic, the reverse is going to be exothermic. And I know we haven't looked at chemical reactions with energy terms in them that much, although we've started to do that. You can see here our energy term, the kilojoules of energy, is on the reactant side. So currently this reaction, which we're moving from left to right, has energy going into it. So this is endothermic. And then the reverse would then be exothermic. I'd be producing energy instead of taking it in if I reversed it. So we are going to be looking at and identifying some key specific spots on these potential energy diagrams. And so you might make a little sketch off to the side of that chemical reaction where we just wrote that endothermic, exothermic, where we can label all of the key areas. You can also label them on the diagrams that you see below, but these are the areas that we need to be able to identify on all potential energy diagrams, and you'll see kind of some examples of what you're going to be asked for on the next page. But if we just draw a simple hill diagram, potential energy diagram, and think of this as having that chemical reaction that we saw up above written underneath it. That's what I was saying about the reaction coordinate or reaction progress. As we move from left to right, we go from having our reactants to having our products. And those are the first two spots you always need to be able to find on this diagram. And I'm going to have all of the important spots show up all at once here. But the two that you should always be able to find is our reactants are always the very, very beginning, and the products are the very end. You can see that the arrows here is the total amount of energy from zero to the line at the very beginning of my reaction is the total energy of my reactants, and same with my products. It goes all the way from the bottom axis to the line of that potential energy diagram. So beginning and end are important points. And that tippy top part of the hill in the middle is also one of our important points. That's what we call the activated complex. And that's generally kind of the arrow. It's the middle of our reaction. That's where all our reactants and all our products are kind of halfway in between forming and being produced. So that is always going to be the highest energy point on our graph. It's what we call the activated complex, the tippy top of that hill. And once again, that line, that arrow, is the total energy at that point, is one of the things that we might be asked for or needed to measure. Now, the only other two things we need to be able to find or measure or quantify on these potential energy diagrams is activation energy, and that's depicted by point B. And this is actually what we need to fill into that blank right there. The activation energy is the minimum amount of energy required to start a reaction. Sometimes it's abbreviated EA, like you see in the exothermic and endothermic examples down below. This activation energy is the amount of energy needed to get from the energy the reactants have here to that tippy top highest energy point of the activated complex. So because it's always going to be the difference between that activated complex and the reactant energy, we can subtract the activated complex energy minus the reactant energy, and that will tell us our activation energy. This is just the energy needed to get that reaction going, get it started. In people terms, 2 cups of coffee is my personal activation energy. It's not the total energy I have when I'm most active. I do bring some of my own energy. My body makes some energy for me. But I need those 2 cups of coffee to get up and get moving and to get going in order to be active. The other point that we need to be able to find and quantify is D, and that is the enthalpy term, that delta H that we've seen and talked about over and over and over again. Our potential energy diagrams can help us find that as well. And just like before, in order to find that, we're going to be taking the product energy minus the reactant energy. So you can see that depicted here. It's enthalpy is how my energy changes throughout the course of a chemical reaction. So it's the difference between where I'm starting and where I'm ending. But just like always, we do final minus initial, products minus reactants, so we can get that sign correct. And we're going to focus on those signs a little bit more when we look at our exo and endo graphs here. So we are going to see some examples about finding these values and quantifying these things for our forward and reverse reaction on the next page. And so we'll come back to these ideas in a moment, but I do want to compare and contrast exothermic and endothermic potential energy diagrams. And a lot of what we're writing down here, we've kind of already seen and talked about before, but these potential energy diagrams help us see it a little bit better. So, of course, exothermic reactions, as the chemicals are reacting, if it's exothermic, the system, my chemicals have energy exiting them. They are losing energy. And so here you can see that our reactants energy, wherever I started with, whatever that number is, my products energy are lower down. See, because energy has exited the system when I was forming those products. So they are at a lower energy state. That means energy is being released. And if we write down, like we said before, energy is moving from our system to the surroundings, then what this is going to mean for our delta H, for exothermic reactions, we're always going to have a negative delta H. And we can see that here, the difference between where my energy, my reactions energy, is starting to ending, it's going down. So this must mean that the overall energy change is negative. And of course, if this is releasing heat to the surroundings, then that is going to feel hot or warm because there's more energy coming out to where we can feel it. Endothermic is going to be the opposite. Here you can see visually that our products have more energy than our reactants have, because during the process of this chemical reaction, more energy went into our system. Energy was absorbed into the system from the surroundings. And because more energy was going into the system, that meant that it is gaining energy, meaning a positive delta H will always be seen. And you can see that our overall energy is increasing from the beginning to the end of this reaction. And even though you might think more energy would feel hot, remember that this is potential energy. This is stored energy. So the energy is being stored more. It's going away from where we can feel it into those chemicals, into those bonds where we can't feel it. So less heat, less hot, means that it's going to feel cold. Now, the last little lines that we need to fill in on page 8 is about a catalyst. You might have heard the word catalyst or this word enzyme in biology. These are some molecules or substances that lower the activation energy of a chemical reaction. That means that this activated complex up here is being lowered, which means that that activation energy, the energy needed to get active from the reactant level up to the top of that hill, is also decreased. So it takes less energy to get going, and that means that it can get going faster. And so this overall increases the rate of our chemical reaction. Notice that it does not change the delta H. My reactants and products energy are still exactly the same. The only thing that gets changed is the total energy at the activated complex. It makes that more stable, lower energy, easier to happen, so it'll happen faster. Now, you need to be able to look at these graphs and tell whether they're endothermic or exothermic, and these should be pretty quick. Just look at the general kind of starting point to ending point. I'm starting higher than I'm ending. Energy is leaving. I can also see that it's showing me I have a negative delta H there. That means that this was exothermic. This one is also going down from beginning to end. Just a little bit less, but that does mean that that is exothermic. And then this one is going up from beginning to end. So this is endothermic, exothermic, endothermic, and endothermic. So you need to be able to recognize these graphs and quickly classify them as endo or exo. But we also need to be able to look at a graph with numbers at the side and be able to provide values for these different points that we have just talked about in our reaction progress. So I'm going to go ahead and label those points here one more time, just in case you didn't write them down before. This is another good place that we can write them. So first place to mention is where our starting point is, reactants at the beginning, products at the end, activated complex in the middle, and then kind of comparing these different values is going to get us our last two. Remember that our activation energy is the activated complex minus the reactants energy, and that enthalpy is products minus reactants. So as we start trying to find our energy content of the reactants in the forward reaction, well, that's just 80. The products, if I follow that over, is at 160, and the activated complex looks like it's at 240. And in order to find our activation energy, I'm going to have to do 240 minus 80, which is 160. And then delta H enthalpy is going to be products, which is 160, minus reactants, which is 80. So that is 160 minus 80 is 80. And that is a positive 80. You don't have to write the plus sign, but I think I'm going to, because that helps me be more confident that this is an endothermic reaction, because that is a positive sign. So just about finding those values straight off of the graph. And then if we talked about the reverse reaction, this is the same reaction, but what we're going to do as we're labeling things here is label our reactants as here and our products as here. That's the only thing that has really changed about this reaction, is now we're going in reverse. The activated complex is still up at the tippy top of that hill, so this is still the total energy to that point. But now we have to be careful as we start talking about the differences between these points, because as we try and find the activation energy, then that means that we're trying to find the difference between our reactants and the activated complex, which is now over here where our new reactants are. And then our delta H is going to be products minus reactants still, but because my products and reactants have switched places, this isn't necessarily going to be exactly the same. So after I have this stuff labeled for my reverse reaction, then most of it is really just about reading stuff off just as easily as I did before. Now my reactants have an energy of 160, my products are 80, my activated complex is still 240. But now as I try and find the activation energy, 240 minus 160 is going to be 80. And then our products minus reactants here, 80 minus 160 is going to be negative 80. And now it is important that we write that sign down. It has to be negative, and that does prove that this is exothermic because of that negative delta H. And because it's the opposite of our endothermic graph previously. So the next page is a worksheet that we're going to be doing in class, and it does have some little twists in it where we're not just going to be reading numbers straight off of it quite like this. We're going to be using some values to help find other values and filling these out and drawing a couple of these graphs, just simple sketches as well. So it does get to be a little more complicated than this, but not too bad.